Good morning, everybody, and welcome back to non-Euclidean geometry. Plan for today, I want to finish off this packet. Talk about on the history of the parallel postulate proof. I remembered what the third piece is. My next office hours are on Monday after class and from 2 to 3, the usual times. I was thinking about, do I want to give them a homework assignment that's due Monday or Wednesday after Thanksgiving? Decided, no, you all probably have enough work for your other classes right now. So here's the plan. Stan. You'll have a quiz the week after Thanksgiving. I'm thinking on Wednesday. It'll be over kind of the proof of the parallel postulate stuff that we're talking about. And then after that, it'll just be the final. Final, I already know. Speaking of which, let me ask you about the final. It says in the syllabus, apparently I put in the syllabus that you're getting an in-class final exam. Let me ask you, would you rather have an in-class exam or a take-home exam? With the idea that take-home exam would have harder questions on it, but you would also have a week to work on it. In class 100%.
Grade our take-home so that I can know.
You will have your take-homes back probably Monday after Thanksgiving. I'm just going to be honest with you.
I would rather have a take-home based on the way all the other exams fall.
Would you like to vote on this after you get back your take-home exams?
Yes.
Okay. I'll put it to a vote after you get your take-home.
Is that going to give you enough time to write anything?
Because yours isn't due until Thursday. That would give me 2 days to write everything. Yeah.
Okay.
Sure.
Thank you for being concerned with my own sanity.
Don't worry about it.
Yes, I know why. Any questions or comments before we get started for today? Okay. So last couple classes. For our last class and a little bit of the previous class, we were looking at this idea of can we use the notion of equidistant locus from a point to a line to kind of somehow redefine parallel lines in a way that would allow us to prove the Euclidean parallel postulate. And it turned out that the answer was no. That if you tried to redefine parallel lines, that's only equivalent to our standard definition of parallel lines in a semi-Euclidean plane, which is not the same as a Euclidean plane, and so that's not quite enough to get you something logically equivalent that can be used to prove the parallel postulate. So now we're going to fast forward 1,000 or so years to Wallace, Thomas Wallace, I believe. Mathematician who came up with another way to try and prove Euclidean parallel postulate using the notion of similar triangles, where we're going to say that two triangles are defined to be similar, where similar is like a weaker version of congruent. They behave somewhat the same, but not as much the same as they would need to be congruent triangles. Two triangles are similar if their vertices can be put into a one-to-one correspondence. So all their corresponding angles are congruent. In other words, they satisfy the conditions to have someone come and tow their car for them when they get a flat tire. AAA. AAA, the angle hypothesis. So as a quick example, close enough. Yes, Celine?
I forgot to ask you about the joke.
Okay, ask me about a joke.
You gotta have a joke.
Dog one day is out herding sheep on a farm, gets them all back into their pen, and says, reports back to the farmer and says, all 40 sheep are accounted for. Farmer is perplexed, says, 40 sheep? I thought I only had 39 sheep. Where'd that extra sheep come from? The dog responds, well, I rounded them up.
Thank you.
I claim these triangles are approximately similar because we can find a pair of vertices. We can take each vertex in the first triangle and match it up with a vertex in the second triangle so that the angles at those vertices are congruent to each other. So let's start with A. Jack, which vertex in the second triangle would you guess is congruent to angle A?
I would guess F.
You would guess F. That is what I intended with my drawing. So good guess. Emma, how about a vertex that you would say looks congruent, or an angle in the second triangle that looks congruent to our angle at point B here? E? E, guess. And then, Lacey, how about C here?
D.
Good old process of elimination. Yeah, so we can say here that angle A is congruent to angle F. Angle at B is congruent to our angle at E. Our angle at C is congruent to our angle at F. And if we combine all of these, that's enough to then say triangle ABC is similar to triangle DEF. And this little squiggle symbol, this tilde, is oftentimes used as a shorthand for saying triangles ABC and triangles DEF are similar to each other. Because there exists a way to kind of pair up the vertices of the first triangle with the vertices of the second triangle in a way that makes all of our angles the angles are congruent. So, question. Is this enough to necessarily tell us if the two triangles are congruent? If there exists a way to pair up their vertices so that the corresponding angles are congruent to each other? Right?
No, you need to know at least one set of sizes congruent, if you want to say.
Yeah. In general, we can say that this is not enough to guarantee that the two sides, that the two triangles are congruent just because they're similar, because there's no guarantee that the side lengths will have to match up to be congruent as well. So in other words, AAA does not work as a way of determining if two triangles are congruent in the same way that side angle side SAS does, or ASA or AAS or SSS. We have that sort of list of 4 different triangle congruence axioms / propositions in a Hilbert plane for if you know these 3 things are congruent, then the rest of the pieces are congruent, and the two triangles have to thus be congruent to each other. Turns out that those 4 did not include angle, angle, angle for a reason, and that's because just knowing that your 3 angles are congruent in each triangle does not mean that the triangles themselves have to be congruent. Here's a counterexample. Maybe a little bit more explicit than this one. These are 2 triangles that I would argue are similar to each other in that this angle is the same as this angle, they're right angles. This one's the same as this. This one is the same as this angle. But these are very clearly not congruent triangles, even though all their angles are congruent to each other, because the side lengths are very much not congruent. you do, as Lynn pointed out, we do need to know at least one pair of sides is congruent in order to say that the triangles are congruent as a whole. If we knew that, like, say, these two sides happen to also be congruent, then we could apply something like angle side angle to say that the two triangles would then have to be congruent. But without the knowledge of at least one pair of congruent sides, all that we get is similar. So, moral of the story is, congruent triangles are always similar, but similar triangles are not necessarily going to be congruent to each other. Any questions or comments about similar triangles? So, Wallace had a proposition that said, aha, we can use the notion of congruent triangles to prove the Euclidean parallel postulate within, say, the Hilbert plane, or because Hilbert wasn't around yet, in the sort of geometric models that we would eventually call Hilbert planes. And so what Wallace proposed as a postulate he wanted to assume is that given any triangle ABC, and any segment DE, there exists a triangle DEF such that triangle ABC is similar to triangle DEF. So in other words, if I have a triangle here, let's say ABC that's pre-existing, and if I have some other segment, let's make it a little shorter so it fits on the board, DE, according to Wallace's postulate, if Wallace's postulate is true, I should be able to construct at least one triangle with this side as a segment and having that triangle be similar to the original triangle. Basically, I should have some way to pick a point F that'll make DEF and ABC similar triangles. And I would say, I would pick my point F to be probably about here. That according to Wallace's postulate, there should be a way to place down a vertex so that this triangle and this triangle are similar no matter what segment DE I pick. If I pick this DE, I can construct a triangle similar to the original one. If I pick this DE, I can construct a triangle, this with dotted lines, D prime, E prime, F prime, that's similar to the original one. Similar, again, meaning all angles are congruent. And that should be true no matter what other segment DE I were to start with. So what do you think? Does Wallace's postulate seem like a reasonable thing we would like to be true in R2? See, at the beginning of the semester, you would all say, oh yeah, Dr. Gerstle, duh, that feels obvious. Now you're all have learned to be much more skeptical when I throw planes out like that. Let me ask a different question. If we're looking at R2, if I had a triangle ABC like this and another segment DE, and another segment DE, would this triangle we could construct on DE similar to ABC necessarily be unique? Right?
No, you can just draw it on the other side.
You just reflect over DE and get a second triangle like that. Yeah, I'd say it's not necessarily going to be unique as such, But Wallace's postulate doesn't make any claim about uniqueness. It just claims that in any triangle ABC, any segment DE, there exists a triangle DEF similar to ABC. And when we claim there exists a triangle, it doesn't. That just means there exists at least one triangle that'll get the job done. So yeah, I would definitely be taking issue if you tried to claim uniqueness, because I would say, ha! Counterexample. But yeah.
One of the things I'm thinking about is U, so the unit disk. If you have a line that's sort of, I don't know, very large in the center, almost like a diameter, then you could have your ABC triangle be like a very pointy triangle somewhere in the middle, so that
A
there's
very
not enough
pointy
room.
triangle.
How do I describe it?
How about this?
Yeah.
Yeah. Yes, very pointy triangle. And then,
Good luck trying to construct, if this is, let's say this is D, this is E, and you're saying good luck trying to construct a triangle on DE that's similar to ABC here?
yes.
Yeah, I think you'd have a hard time trying to do it so that ABC is similar to DEF, especially if you want the AB side to kind of correspond to the DE side. Like these side lengths are so long compared to this one that if we tried to do this in U, we would have to get something that kind of extends outside the unit disk, is your claim, Jack?
So it seems like you need some kind of model that has the congruence axioms to do this.
Yeah, we would need some notion of having congruence axioms to play around. Luckily, U isn't a Hilbert plane, so that doesn't automatically invalidate it, but that certainly gives rise to some, maybe a little bit of skepticism, I would say. Right?
Well, I have a question. So, do we have to have DE be the similar side to AB? Because technically, you could draw something where DE is similar to CA.
Could we?
Yeah.
Something like that, perhaps?
Yeah. And because you can flip it on either side of a line, it doesn't matter how close you get to the edge of the circle or the unit disk, you can always do it on the reverse side.
Trying to think. Well, the definition of similar that we use says that if ABC is similar to DEF, I guess the definition we use doesn't say that the sides have to correspond in exactly this order. That AB doesn't have to be the side that kind of matches up with DE in the sense. I guess that's true. That's an interesting question. Now I'm trying to think, can we still construct a triangle so that no matter which side you chose to be your DE correspond, or which side you want a DE correspond to, it would still have to break something. Right?
I think it would still work if you make, let epsilon be absolutely tiny and put D and E right up against the border, right?
Let epsilon be very, very tiny. Class do you think
And
this
greater than
is?
0. And then you have AC congruent to AB, right? So DE is practically a diameter, and any other segment is not going to be a diameter. Does that make sense?
Well, it's put an equilateral triangle like that.
No, I was using the same triangle.
Oh,
Even if it's tall and skinny, right?
Oh, you're saying you
If
wanna change
DE
DE
is so
around.
absolutely long that any line going from E to anywhere else is not going to be a diameter. So it can't be as long.
Gotcha. So
So
basically you're saying that if you want to assume that
Yeah.
construct an isosceles triangle, let's say,
Mhm.
we already know that this can't correspond to AB, and that if it corresponded to that,
Because it yeah. You can't construct another diameter for that.
there does not exist any other point in the disk such that DE is congruent to the segment for E to that other point.
Yeah. If you made them close enough to the wall.
If we were to take some
You can just put it on the wall.
epsilon neighborhood of our
Doesn't the unit disk include the?
unit disk explicitly did not include the wall.
And then, yeah, it does just fail for an equilateral if you have you have the length DE where we have it now.
Gotcha, just because, I don't want to dive too deep down this rabbit hole because I think we're
Epsilon.
Yeah, because I think we would have to dive into something like, all right, let D be arbitrarily close to the boundary, fix some epsilon greater than 0, can there exist another point? And I think you're right away, but I think actually proving that is not something I want to do
Yeah.
in this class. Good off that conversation maybe. But yeah, basically this, I think what we can show is that this isn't going to always work in the unit disk model U. The Wallace's postulate would not hold in U, even though it feels like intuitively maybe it should hold in R2. So it turns out that if you assume Wallace's postulate, and if you're working in a Hilbert plane, you can actually prove the Euclidean parallel property. See if we can prove that. That is what I would like to prove. And this is Wallace's proof as part of his proof of proving the Euclidean parallel property. So, proposition. In a Hilbert plane, Wallace's postulate implies the Euclidean parallel postulate. That if I have a line and a point not on that line, then there has to exist only one line through the original point that is parallel to the original line. So let's see if we can prove this. So we're going to start off with a line L. And I'm going to have a point P here. And our goal is going to be, say, if we assume that we're working over a Hilbert plane, and if we assume that Wallace's postulate holds true, there cannot exist multiple lines through P that are both parallel to L. We already know in a Hilbert plane there has to exist at least one line that'll get the job done. But according to this, if we assume Wallace's postulate, there can't be multiple lines through P that are going to be parallel to L. Let's prove this. So to start, we're going to say that given a point P not on L, let N be constructed parallel to L, or not N, M. And according to what the book says, via the standard construction. What does that mean? Does anybody remember how we came up with there has to exist a line through P parallel to L in the first place? Huh?
That you find a perpendicular to P and then a perpendicular to that perpendicular?
Exactly. We draw, what we do is we start by drawing a perpendicular to P through L. And then we draw another perpendicular from, and we'll call this point Q. And then we draw a perpendicular to P through the point, or through P that's perpendicular to PQ. And that's going to give us our M here. So if you're reading the book and the book asks about, like, here, make a line that passes through P parallel to L via the standard construction, this is what they mean. Drop a perpendicular from P to L, and then take a perpendicular to that through P, and via stuff we saw back in our neutral geometry packet, the line M here that we're going to get is going to be parallel to L. And now we're going to let N be a line through P. what would we like to show about n? If we want to prove that the Euclidean parallel postulate has to hold. What would have to be true about our new line n that also passes through P? What?
It must intersect L at some point.
Yeah, if the parallel postulate's true, it's impossible to have a second line through P that intersects L. And I guess we should probably say n not equal to m. Because obviously if n and m are the same line, then n can be parallel to L. But we want to show if we take any other line n that passes through P, it's going to have to intersect L at some point. In other words, we have to show that n cannot possibly then be parallel to L in order for the Euclidean parallel postulate to hold. So, if you recall, this is very similar to how we started constructing Proclus's proof of the Euclidean parallel postulate. It started off basically the same as this. We started by assume we have a line L, point P not on L, n be a line through P parallel to L. And then if we construct another line n through P, it show that n has to intersect L. And then Proclus from there went on to prove n and L had to intersect using some questionable methods. Here's where we're going to diverge from Proclus's proof, though. We're going to say, as before, consider a ray of n between PQ and a ray of m from P. So in other words, we're basically saying, assuming n and m are not the same line, then one ray of n is going to have to be in between this ray here and this line segment there. Assuming n and m are not the same line, one of the rays of n has to be between PQ and some ray of n. Either this ray or potentially, depending on the configuration of n, if n's going from like down left to up right, we could have a ray like this of n instead. So now that we have that, we're going to say for any point r on this ray, this ray of n, let S be the foot of the perpendicular from R to PQ. So in other words, we're saying pick some point R on this ray. It doesn't matter where for now. And then from there, we should be able to find a point S on the ray, on the segment PQ, that's going to make this into a perpendicular. We're dropping a perpendicular from R here down to the segment PQ. And now, here's where we're going to get fancy. PSR here is going to form a triangle where one of the segments happens to kind of coincide with the segment PQ here. And PQ is going to be some segment in our plane. What Wallace did next is he decided to apply his postulate at this point to the triangle PSR in the segment PQ to basically get a triangle where PQ is one of the sides of this new triangle that is similar to the triangle PSR. So here's where we're going to use Wallace's postulate to say, by Wallace's postulate, there exists a point T such that the triangle PSR is going to be similar to the triangle PQT. right here, we're assuming PQ is sort of our DE segment in Wallace's, in the statement of Wallace's postulate. PQ is our DE. PSR is our original triangle ABC. And so according to Wallace's postulate, we should be able to construct a triangle here on PQ, meaning we should be able to find some other point in our Hilbert plane T, such that PQT, wherever T ends up being, I don't know, for now I'll draw it here. So that triangle PQT is similar to triangle PSR. Megan, you look very unhappy.
That just took a turn that I wasn't expecting.
It's like a twist. Why is that?
Because I thought we were just gonna make PS bigger than we on that one.
We're just gonna do something like, oh, just make this line segment bigger and bigger until it lies on this
Yeah,
line?
that's what I was expecting. So.
As I say, that's essential, or it's not exactly the same, but it's very similar to what Proclus tried to do in his proof of the parallel postulate. But then we ran into issues like, oh, let's extend this so that eventually this has to match up. Well, how do we know if we make this longer and longer, it'll have to match up? And lead into the same sort of problems we saw on Monday when we were discussing Proclus's proof. So now, we are indeed taking a twist in our proof. Well, Jacob, you ended up closer to the door. So now, we're going to say, where does this point T have to lie? Does Wallace's postulate tell us anything about where the point T happens to be located? That?
Not directly, but we might be able to tell if we figure out which angles correspond to which other angles.
Yeah. Well, certainly we would want to say which angles correspond to which other angles. And I purposely want to write it in a way that PS corresponds to PQ, PR to PT, and SR to QT. It's going to be the way we do it. But theoretically, we could have a T here, we could have a T here, we could have a T way down here. Okay, that one's probably not going to work. But Wallace's postulate doesn't tell us anything about where this third point T is going to be located. Up here. So we're going to say, without loss of generality, T is on the same side of PQ, of the line PQ as R. So we're saying, well, we don't know where T is going to be, but we want to assume that T is on the same side of this vertical line right here as the point R, for reasons that'll be important. But Dr. Gerstle, what do you mean without loss of generality? What if the T we get from Wallace's postulate is actually over here? Well, but without loss of generality just means, we can assume it. These are on the same side, because if they're not, we get a triangle PQT where the T's over here, just reflect it across the line. And then we'll end up with a triangle that's congruent to the one we would get here. This PQT is congruent to the, okay, fine, T would actually need to be in the middle of my PF. But if we reflect across this line PQ, we can get a triangle where T and R are on the same side of the line PQ. Maybe our T is way up here, but at least T and R are on the same side of the line PQ. And if the triangle we get doesn't have that property, we can just reflect it over the line PQ to get a triangle PQT that does have that property.
And is the reason why we can say you can reflect it because you can just apply Wallace's postulate again, but to sort of like the same line of the triangle?
Yeah, essentially.
Okay.
So now we have a triangle, and our goal, here's our goal, by the way. What we're going to show is that T has to be on the line N, and T also has to be on the line L, which is going to tell us that line N and line L are going to intersect at the point T. That's going to be our goal. Let's do this. So we have triangle, PSR, PQT that are similar. T and R are on the same side of the line PQ as the point R. And then we can say that from how we constructed this triangle, angle TPQ is congruent to angle RPS from how we constructed our similar triangles. So that if we wanted to construct them in a way that made PS match up with PQ, PR match up with PT, SR match up with QT, in how we applied Wallace's postulate here, then we can assume that the angle from T to P to Q, so I guess this angle right here, has to be the same as the angle from R to P to S, which is that angle. And that's just part of similar triangles. If our triangles are similar, then we have to have matching pairs of congruent angles. Not necessarily sides of our triangle, but angles. So angle TPQ is congruent to angle RPS. And then we can say, but since these angles have a common side, of PQ or PS, basically saying that these two angles share a common side, meaning their triangle PTQ and PRS both have a side that lies on this segment here, PS or PQ, however you want to refer to it. And T and R lie on the same side of PQ. The line PQ. This forces that the ray PR is going to be equal to the ray PT. In other words, since both the segment from P to T and from P to R, T and R are both on the same side of PQ here. We have this angle is congruent to that angle, and that this side is the same. It turns out one of our congruence axioms is going to guarantee that the only way for T and R to be on the same side of P and Q, and to have that these angles formed from Q to P to T versus Q to P to R to be the exact same angle, the only way for that to happen is if T and R happen to be on this same ray here, meaning these two angles are exactly the same angle. Which congruence axiom guarantees that? Okay?
Is that 4?
4, the one that says, given any angle at any ray, there exists a unique point, there exists a unique ray on each side of that original ray that makes an angle congruent to your original angle?
That sounds great.
That sounds great to me too. Yeah, so in other words, PR and PT, the ray going from P to R has to be the exact same as the ray from P to T. And notably, if T happens to be on this ray, so if T's down here, what does that tell us about the relationship between our line N here and the point T? If the ray from P to R is the same as the ray from P to T, and PR is a ray on the line N,
Then T has to lie on the ray PR.
yeah, exactly. Then T has to lie on the ray PR, and thus T has to be a point on the line N. Because PR, the ray PR is just part of the line N. It's a subset of it. Thus, we can say T happens to lie on the ray PR, and thus N. So in other words, congruence axiom 4 tells us that the only way to get these similar triangles that to happen here is if t happens to be on this line here, n, which yeah, so t is on it. Any questions or comments thus far? John?
Sorry, where does the PR equals PT come from?
Congruence axiom 4, which basically congruence axiom 4 says something like this, where if we take our line PQ here, or let's just do a ray going from Q to P, and we have some angle, some fixed angle, which here is going to correspond to the size of the angle PTQ and PRS. It says that there should exist a single ray on the right-hand side of this line, that if we draw out that ray will give us something congruent to our original angle here. And so basically, if this angle is the same as that angle, meaning we have a line here from P to R, and we have another angle on the same side of PQ here, another point T where this angle is also congruent to that one. Congruence axiom 4 says the only way for that to happen by uniqueness of this ray is if the ray from P to R and the ray from P to T are the exact same ray. You look skeptical still.
Yeah, I guess I'm missing something because.
So the fact that we know that our angle from R to P to Q versus T to P to Q just came from the fact that came from our similar triangle construction. The fact that triangle PSR and the triangle PQT are congruent triangles to each, or not congruent, sorry, similar triangles to each other. That tells us that the angle from R to P to Q is the same as the angle, or technically from R to P to S is the same as the angle from T to P to Q, and then the angle from R to P to S is the same as the angle from R to P to Q. So we get two congruent angles here, and so in other words, if we kind of take our angle RPS and just kind of move it in space over to the side here, we get both of these angles are congruent to this thing. What congruence axiom 4 tells us is that if we have a ray here going from Q through P, or sorry, P through Q, let's get my angle, let's get the rays right, then according to congruence axiom 4, there exists a unique ray passing through P on either side of the ray PQ that'll give you that this ray and this ray will form an angle congruent to whatever's over here. And so if we have that if RPQ and TPQ are both congruent to this thing, then there should only be one ray on the right-hand side of the ray PQ here that's going to form an angle congruent to this one over here. And thus, if PR and PT are both rays that are going to give us something congruent to this angle here, they have to be the exact same ray coming out of P.
I'm still confused, but I mean.
Well, how about we talk about it more after class then? Moral of the story is, what we get from this is that T has to lie on the line pin here. Yeah, this is definitely sort of a tricky proof with lots of rays and angles and stuff flying around here. So now, we also want to show that T has to lie on the line L. And we're basically going to do a very similar sort of idea to show that. We're going to use congruence axiom 4 again. And say that similarly, we know that the angle PQT is going to be congruent to the angle PSR. So the angle from P to Q to T, this angle, is congruent to our angle from P to S to R. Why? Because of our assumption that, or because of our knowledge that this triangle is similar to this one, meaning all the angles have to match up. And so, angle PQT is a right angle. And thus congruent to angle PQV, where V is just going to be in some point down here. So since PQT is congruent to PSR, PSR is a right angle from how it was constructed, so PQT also has to be a right angle. And then since PQV here is a right angle, that tells us that PQT and PQV are both going to be right angles. And then we can say, aha, now we have two different right angles coming out of this ray from P to Q here, both of which are on the right side of PQ. Thus our angle from P to Q to T it has to be the same as our angle from P to Q to V, again, by applying congruence axiom 4. Thus, by congruence axiom 4, our ray from Q to V has to be equal to our ray from Q to T. And so T lies on the ray QV and thus on L. Where here, what's going on? So this time we have a construction going on like this, where here's our point Q, here's our point P, and our angle over here to the side that we're going to be looking at is a right angle. What we're saying is we have a right angle from from Q to P through this point here, V. We have another right angle from P to Q to this other point T here. According to congruence axiom 4, the only way to have an angle on the right side of PQ here, or the only way to have a right angle on the right side of P to Q, both of which are going from P to Q to T and from P to Q to V, congruence axiom 4 says the only way that can happen is if this angle, PQT, is exactly the same as the angle PQV, meaning QT and QV, these two rays, line up on top of each other, which means that T has to be on the ray QV. And thus, T lies on L. And now, I think we can finish this off, because we can say that the point T lies on the line N, the point T lies on the line L. Lacey, what does that tell us about the relationship between the line L and the line N here?
They will be incident together at the point T.
Yeah, they're gonna have to intersect each other, and thus they cannot possibly be parallel lines. Thus, N and L intersect at T and thus can't be parallel. And then I think to wrap up, we can say thus, there can only be one line M through P parallel to L. So the Euclidean parallel postulate holds. And we are done. So in other words, the existence of similar triangles on this given segment PQ, the fact that we can construct a similar triangle PQT here to PSR is going to be what tells us that line N and line L have to intersect. Because congruence axiom 4 guarantees that if we have this triangle PQT similar to PSR, then T both has to lie on the line N and it has to lie on the line L. So in other words, the only way that this can happen is if our line N and our line L intersected at this point T down here. Sorry, I ended up drawing T in like 5 different places in this picture, I think. Because a priori, we don't know anything about where T has to lie, but congruence axiom 4 eventually allows us to show that T has to lie at a point of intersection of the line N and the line L, and thus N and L can't be parallel. Right, we are out of time for today. So when we come back on Monday, we'll finish this packet and start the next one. And talk a little bit, and we'll also start by discussing, we just proved that Wallace's postulate proves the Euclidean parallel postulate in the Hilbert plane. Why doesn't that count as just a valid proof of, why can't we just go home and say, aha, we've proven the parallel postulate. It can be proven. GG, no read. Have a good weekend.